Good morning, everyone. So welcome from the Computational Social Science team of the Faculty of Social Science at CUHK. My name is Qingliang Fan. I am the host for today's CSSL webinar from the Department of Economics. Also, I am the co-leader of the research scheme of the Artificial Intelligence for Social Good at the CSSL. So nowadays, the big data aided by the platform and digital economy and the computational capacities is making a fundamental impact on the social behavior and also policy making. Inclusive finance, personalized medical treatment, e-commerce, just to name a few. The recent development in the computer science and engineering has also caught attention from economists and social scientists, including, of course, our speaker today, Professor Luo Ye. He is Associate Director of the Institute of Digital Economy and Innovation at Hong Kong U Business School. Ye is actually made in MIT. He got his bachelor's and PhD degrees from there, and he was a well-established econometrician, statistician, maybe also call him data scientist, because his work has been widely applied in many industrial needs. Okay, so without reading his long list of the published work, I will actually now hand over the floor to Luo Ye, since we're all very eager to learn from his new research in endogeneity in reinforcement learning, titled The Self-Fulfilling Bandits. Now, please, Professor Luo.
Okay, thank you very much. First of all, I want to thank Qingliang for inviting me to, to this, to give this talk today on the, on your platform, and I feel very happy to introduce our latest work to all the audiences. So today our topic will be the self-fulfilling bandits, dynamic selection in algorithmic decision making. Okay, so this is a joint work with Jin Li and Xiaowei Zhang. Both of them are colleagues of HKU Business School. Okay. So I want to start with a few motivating examples on on the question that we're trying to study. In this research. So basically, if you, on the left-hand side, this is my search results on Amazon. So if I open my Amazon, so, the app will recommend a few books to me. For example, the first one will be The Myth of Artificial Intelligence, why computers can't think, blah, blah, blah. And second is also like artificial intelligence and so on. You can expect that, different people may have different recommendations. The question is, why do I get these sort of recommendations when I open my app, right? The simple answer is there's an algorithm that, runs on the Amazon platform that learns about you. So that's the simple, that's the very simple answer to it. Okay, and so you can sort of imagine that how algorithms will affect our lives, daily lives today, and of course daily lives in the future as well. Okay, and on the right hand side, I'm going to give you a simple example on, for example, hiring. There's a very famous research paper these days in economics, by a bunch of economists from MIT. So they are doing a paper called hiring as exploration. So what does that mean exactly? So basically, imagine that for a firm, right? So you try to hire the best people you want. However, you don't really know where the people that are most suitable for your firm are, right? So, if you look at companies like Tencent, like Tencent, right? Most of the employees of Tencent are actually not graduated from the top schools in China like Tsinghua and the Beida, right? So actually they graduate from some other schools. So the question is, how do you find the most suitable employee to your firm, right? So this is also a question that the firm needs to learn about what's the best choice they should they can have before they make the decisions, right? And as a result, so sometimes the firm will have a sort of strategy that, the firm will sort of randomly choose to interview some of the candidates. I mean, regardless of what these people looks like. I mean, like graduate from very high ranked university or low ranked university, have high GPA or low GPA, like this person can have a lot of like social activities during his or her 4-year education at college, or he or she maybe like staying at home and like doing programming all day. So which kind of person is the most suitable type to a specific firm is actually, we can say, I mean, so some sort of domain knowledge and has to be learned by the firm gradually. And and nowadays a lot of big firms, they also use algorithms to search for the suitable, at least they use algorithms to do the so-called pre-screening. So there's a some sort of algorithm that's running on the HR system that selects certain type of candidates which they think may have a higher probability of fitting with respect to this company's needs, okay, and so on. So the feature of modern organization decisions is one of the key features is personalization. So the decisions will depend on individual characteristics. Like just I said about the Amazon case, so everybody will have their own recommendations, rather than in the old days. I mean, we open the TV and we're all gonna watch the same sort of programs, right? So nowadays we have our own recommendations. So these recommendation decisions are made based on observed individual characteristics, of course, okay, like age, gender, your past browsing history, of course, or your past purchasing history for e-commerce, let's say, and so on, okay. And now I want to draw, I think the most important, key feature between a more traditional sense of data and analytics, or whatever you call, right, data science or econometrics or whatever you call it, or statistics, right? So nowadays we are more or less in the so-called online learning environment, especially for these like modern digital firms, digital economy, okay. So on the one hand, these digital economy, so these online platforms, on the one hand, they are statisticians or econometricians or whatever, they observe data and they sort of estimate some sort of models, and they make decisions based on those models. So this is more like the picture on the left, so from data to decision, and this is typically we call it as an offline environment. So you collect data first, and then you make all the estimations based on whatever you observe. Of course, the key underlying assumption here typically is that the data generating process is more or less fixed, okay. So you face some sort of a stationary environment, and you collect data from there. Typically the data will be IID or strongly mixing or whatever, it has a fixed sort of a data structure, okay. And this poses the backbone of traditional statistics or econometrics analysis, okay. However, we are talking about a new regime. So in this new regime, on the one hand, the decision makers, they collect data and then they make decisions based on what they observe, just like the left picture here. But on the other hand, the decision makers are constantly making decisions within the environment, which may perturb the data generating process. Or, let's make it this way. The decision maker themselves, whatever they make, whatever, the decision they make will be part of the data generators, okay? As a result, decision maker, on the one hand, learn from data and make decisions. On the other hand, what kind of data do they observe depend on the decisions they have already made. No matter whether it's the decision that they're making right now, or it can be the a sequence of decisions that they have made in the past. Okay, and therefore, a kind of feedback loop is sort of the novel part of this regime. So you see that, so we call this the online environment, okay? So the data will affect decisions. You observe data, you estimate some sort of models, and you make decisions. So that's the traditional type of data science we know, okay? But on the other hand, especially in social science, in business and in the related areas, your decision will likely to affect the future data generating process. Let me give you a simple example on, on finance, right? So think about a central bank. Okay, a central bank. When I was back in MIT, so I sometimes I talk to these like macroeconomists, and the macroeconomists, they always discuss like the Fed policies. Okay, so the policies of Federal Reserve, for example, it's based on like 300 or 400 different kind of so-called, they call it structural models, and they estimate the structural models in some ways based on what they observe. And then they make policies based on that sort of, this is just one conjecture, okay? However, because let's imagine that the Federal Reserve adjusted its, monetary policy, let's say nowadays, the Fed is sort of increasing interest rate, right? Which has a big impact on everybody's daily life. So, when they increase the interest rate, the macro variables they're going to observe in the future is very likely to be different, to have a different DGP than the macro variables they observe in the past, and so do the macro behaviors, like firm investing behaviors, and so on and so forth. Okay, so that's a typical kind of example where this decision maker is sort of affecting what she's gonna observe in the future. Okay, and now I want to push for this very simple type of model, which is a very stylized way of thinking about a dynamic decision making problem, which we call the so-called contextual bandit problem. Okay, so the typical type of bandit problem here, think about a squid, right? Has a lot of, many different arms. And, there are many different of these gambling machines, which we call them bandits. So every bandit has, so every arm is like a bandit. And imagine that every machine has a, reward to this agent, okay? And ideally, you want to choose the machine that has the highest reward, and just keep on playing that arm, all right? But you don't know which machine has a higher reward than the others in the first place. And therefore, it's a sort of learning problem in the very beginning. The most simple, the simplest kind of model is so-called mean model, where you try to find one arm that has the highest mean reward. Okay. A slightly more complicated scenario is where you have a contextual. So you have a context. For example, it can be either, sunny or rainy. Maybe when it's sunny, this army has the, highest, reward, in its expectation. When it's raining, maybe is the other one, okay? And therefore, you want to learn about, so given the so given the context, you want to sort of figure out, you know, which arm is the best one to pull. Okay, so that's why we call it contextual arm. You know, or that's why we call it contextual bandit problem. Okay, so basically we need to decide which arm to pull. For example, you know, which product to recommend to a certain specific user, because we observe the characteristics of the you know, of the particular user. So for example, you know, for a male, we may want to recommend a razor, right? And for a female, we may want to recommend a shampoo. So that's a simple kind of way to understand this sort of problem, okay? And once we pull the arm, we will have an observation of the reward, okay? You know, it could be like, you know, whether, you know, this consumer click the link of the product, or it can also be, you know, the final purchase behavior of the product, just for example, okay? In the end, after you have done like 3 steps, you know, you're gonna adjust the estimate of the reward function and also the decision rule. And then you go back to, you know, the first step, you know, so this is like a sequential decision-making problem where, you know, you are constantly learning from the data, and you are constantly making decisions based on what you observe. Okay, so this is the simple kind of description of the question that we're looking at. All right. And now I want to bring a bit more of the, you know, endogeneity into the game, because in social science we always talk about endogeneity. We always talk about you know, for example, you know, there are, you know, so because social science, human behaviors are so complex, right? There are going to be omitted variables, there are going to be selection bias, there are going to be many of these key issues. I have talked to many of the, you know, like first tier firms in China, you know, I talk to e-commerce, I talk to like that, you know, like pricing departments and so on. And they're all curious about this, because in a more traditional like machine learning sense or statistical sense, you know, you have a label Y, you have a bunch of variables X, and you just predict X from Y, you know, using some kind of black box, you know, algorithm, whatever. However, you know, you know, all of these people who work in these firms, who, you know, all of these people who are in the frontier of business, they all realize that there are endogeneity. Okay. You know, for example, just take e-commerce as a, you know, as a simple case, right? So they realize that, for example, their current policy is to recommend razors to men and to recommend, shampoo to women. I mean, let's just say that. However, you know, the question is that it could be the case that, you know, the man wants to buy razor, for example, it's not because they are men, but because they, you know, of some other reasons. Okay. And if you don't figure out this sort of, like causal relationships, you might get into all kinds of misunderstanding of things. Okay. And therefore, you know, the traditional, like I said, the traditional machine learning literature is to study, for example, in the bandit literature, is to assume that the noise and the covariance are sort of independent from each other. So this is the sort of standard assumption. You know, but whenever, you know, we face like human behaviors, it's more complicated. Therefore, we have the so-called endogeneity problem, quote unquote, in economics. Okay. It could due to many different reasons. Measurement error is one of these. For example, you know, firms. You know, if you talk about, you know, if you talk to, you know, organizations like firms, right? You know, sometimes, you know, the middle manager has a lot of incentive to misreport, oftentimes underreport the cost to the higher, you know, like management team because of incentive issues. Okay. And model misspecification is is another type of reason for endogeneity. You model, for example, you model reward as a linear function, but it could be nonlinear in general, and therefore you are misspecifying the model, and this also creates endogeneity in some sense. Okay. Sample selection is another thing that many people talk about. Think about think about this, right? So maybe you are thinking about launching an advertisement campaign, and you are trying to estimate the treatment effect of this advertisement campaign by looking at data. However, let's say you may choose to launch the campaign on weekends, right? I mean, every Saturday, every Sunday, let's say you pay more money to Google ads and so on, right? Let's just say that. However, I mean, maybe you do see an increase in the sales at the end of the day, but it's probably because on the Sunday and the Saturdays, people have more time to come, right? So this is a sample selection issue, right? So the sample on the weekends are sort of different from sample in the weekdays, right? And of course, at the end of the day, omitted variable is always a key hurdle in social science because like Paul Samuelson said, the first Nobel Prize laureate in the USA, he always say that the models are bound to be wrong. So omitted variable issue is always we always we admit that this sort of problem is always there in economics or social science. Okay.
Oh, Kurt.
Yes.
May I have a very quick question?
Of course, yeah.
Yeah. So regarding this endogeneity, so my quick idea is, I mean, a lot of those applications scenario is in the industry, right? In this platform economy. So my question is, I mean, so what are the obstacles for this A/B testing? Right, it's kind of the classic one to address this kind of endogeneity problem.
Exactly.
I know your case is well motivated for this sample selection issue, which is very common, of course, right? But I mean, I just want to have a kind of a quick response from.
Yeah, exactly. So that's a very good question. Thank you, Qin Liang. So, actually, I'm going to talk about a little bit of A/B test later. But anyway, I can share my whatever I know right now to all of you. So, a few comments on this. First of all, companies are doing a lot of A/B tests these days, like Alibaba or Amazon. They're doing like thousands of A/B tests. Okay, and Huawei is also doing a lot of A/B tests. Like they use like 1% of digital volume on their platform every year to do all kinds of experiments. I mean, 1%. Remember, 1% is actually very, very expensive. Okay, because that means that you're going to recommend you have the risk of recommending the wrong product to customers. When you do these sort of random experiments. Okay, so that's what they do. There are a lot of fallacies of A/B test. First of all, you cannot really control the entire environment. You don't really have a very clean A/B test environment. Like I used to work with Didi, in like 5-6 years ago. And they complain about this. So it's you don't really have a clean A/B test environment in business, actually. Of course, in social science, I think. And secondly, the A/B test is basically to test whether decision A is better than decision B. But you may have like decision C, decision D, or whatever available to you. So rather than finding out the optimal decision, A/B test is more like choosing one or the other. Okay, of course, A/B test can also suffer from endogeneity problems. So if you can just like what I said, if you cannot have a clean control environment, for example, if you cannot really control for sample selection in A/B test, ideally A/B test should be able to control this. But in practice, if you cannot 100% control sample selection issues, then the treatment effect you estimate from A/B tests may be biased. So that create all kinds of problems in A/B tests. But last but not least is that A/B test is very expensive. So one of the key questions that we are thinking about in our own research right now, so beyond this paper, is that from a very economics point of view, okay, so there exists a trade-off between company learning, for example, or organizational learning in the big data environment versus the cost of learning. So people don't talk about cost of learning too much in the past. If you read machine learning or statistical literature, the main focus is on learning itself rather than its cost. I mean, economists think about costs. Okay, I'm going to elaborate on this a bit later, but that's not the key point for today. Okay, thank you for the question. So now I'm going to talk a little bit on how what's the difference between the traditional sense of endogeneity we talk about in social science versus the endogeneity in the online learning environments. Okay, so we're talking about the difference between offline and online learning in the previous slides. Now I'm going to discuss the key differences when you have endogenities. Okay, the main point is that the endogeneity problem can be exacerbated by online learning environments in the following sense. Okay, and that's why we call it, it could be a so-called dynamic selection problem. Okay, so endogeneity can affect the data analysis, outcome of data, of course, if you ignore it, right? So your estimates can be biased, or estimates can be biased if you ignore endogeneity. That's what we know. And when the outcome, for example, when the reward of the arms are biasedly estimated, then the decisions you make based on these biased estimates can be wrong as well. Okay. And when you make a wrong decision, it can further affect what kind of data you're going to observe in the future. For example, I'm going to give you this example that we think is omnipresent, in our life, is that a lot of firms, middle managers, this is typical kind of agency problem. Middle managers, they have a tendency to underreport their costs, and therefore the higher management level will tend to have a higher estimate of the decisions. For example, when they launch an advertisement campaign, the middle manager will say, look, we spent, $1 million, but we have this sort of effects. But actually, they may, this $1 million campaign may take like 20 people to full-time, to work full-time, and this sort of human capital can be allocated in some other, tasks which can generate positive, profits or whatever. Okay, so they don't really report this opportunity cost, and as a result, the higher manager will think, well, look, the reward is higher than we expect, and then let's do more. This is sort of the feedback that you can imagine that leads to this sort of exacerbation of endogeneity problem. So basically, the bias will affect decisions, and decisions may further amplify the bias. So that's the sort of the mechanism we're talking about here. Okay, and I want to, before I go to the main materials of the talk today, I want to do a little bit of a summary of our contributions to the literature. First of all, we identify a novel type of bias, which we call a self-fulfilling bias in the online learning environment, which I'm going to introduce it to you in more details later. Okay. In a couple of minutes. And second, we propose algorithms that not only correct for the bias, but also generate actions that attain low levels of regret. I'm going to introduce what does regret mean to you later. Okay. And third, we develop a technique that facilitates theoretical analysis of online learning algorithms with endogeneity problems. So the number one point here is the phenomenon. It's a self-fulfilling bias. The second one is a methodology that can help us to deal with it. And we hope that, for example, this methodology, this could be one of the solutions to, for example, firms or business organizations in the future when they face this sort of problem. And third, this is a more technical issue because we know that now the data generating process depends on your decisions. And your decisions, of course, is dependent on the past observations. And therefore, this creates a complex dynamic time series, dependency across decisions, actions, and so on. And the question is that, what kind of, unlike the traditional stationary or strongly mixing sort of time series environment, right? So, what we can do about it in terms of its techniques, okay? But today in our talk, I will focus on the first 2 points, and I may just briefly talk about the third 3, or simply ignore it, depending on the time, okay? So the roadmap is following. I'm going to divide the next 1 hour into the following 4 sections. The first section is the introduction of self-fulfilling bias and what kind of phenomena we observe from there. The second one is that we're going to introduce the the instrument variable-based algorithms that solves this sort of bias problem, okay, in a dynamic online learning environment. The third is the theoretical analysis. And the fourth is the simulation. Okay, so when I reach simulation, I may switch to my website because I have some trouble of showing the simulation picture in a PDF file because it's too large. Okay, so it's going to start there for a while. So the contextual bandit problem in the traditional sense is a sequential decision-making problem where at every time t, little t from 1 to capital T, so this capital T can be very large and go to infinity, okay? An agent will observe a vector of corollaries Vt in the Euclidean space of p dimensions. And, she's going to take an action, basically choose one arm, AT, we call it pool arm, but basically it's like choosing one of the arms from a set, like 1 to capital M. The simplest case that we can ever have is M equals to 2. So you have 2 choices. You either go left or go right. Okay. And then it's going to receive a random reward RT. So this RT is a summation of, it can be written as this, but actually, these are indicator functions of AT equals to I. So basically, you will receive mu I of VT as the mean reward if you choose the arm I at time t, okay, and then plus a random noise, of course, okay. So the most popular model that has been used in the literature is the linear model. That's simple. You may want to think about non-parametrics, but you can always use something like a sieve, linear sieve to approximate a non-parametric model anyway. So it goes back to a linear model. Of course, the sieve is slightly more complicated, but so think about a linear model where mu I of v equals to v transpose times alpha I, where alpha I is going to be a vector. So it's going to be a p-dimensional vector that is specific to the arm I. Okay, so every arm has its own, one parameter we call alpha I, right? And the task is to learn about this alpha I, of course, one of the tasks, okay. Again, these are the key applications like recommendations. The VT is here, which you call context variables. Okay, can be age, gender, browsing, shopping history, device. Whether you are browsing the web from a PC, Mac, iPhone, Android, and so on. Okay, and AT will be products, articles, news, for example. So that's the sort of the things that you want to recommend. Okay, and the reward, for example, can be clicks and purchases in the Amazon case, right? Hiring is another one. VT is applicants, demographics, education, work history, and so on. AT is the you want to interview or not. Okay, and the RT is the hiring potential, which is basically at the end of the day, it's the quality of the applicant. Okay. And now I want to introduce the key metric that evaluates an algorithm or a policy in this sort of dynamic context, which we call it regret. So regret is basically the core of at least one of the core metric of evaluating dynamic algorithms. Okay, dynamic learning algorithms. Okay, so oftentimes we will think about a benchmark policy, and in the case of contextual bandit, we can always have a so-called oracle policy. We call it pi star. Okay, assuming that all the mu-i functions are already known. So you know all the mu-i functions. Just assume that. Of course, you don't know in practice. And you can always pick the arm I that maximizes over all the mu-i of VT, given VT. And that's the optimal policy when you observe VT, right? When you observe VT, you just pick the arm that maximizes all the reward, mean rewards across all the arms. So that's the pi star policy. Of course, this policy is unknown. Okay. And then, you want to find, a policy pi that basically minimizes the regret of pi like this. So the regret of pi is the summation from little t from 1 to capital T, the expectation of, so this is the oracle, regret you're gonna get, right? And this is the actual regret you get from this policy. Okay, for example, one of the simple policy pi can be like random policy. I just randomly pick. So imagine that you just randomly pick the arms. What's going to happen? Even if there are only 2 arms, you pick like 50-50. Okay, so there's a 50% of chance that you're going to do it right, but of course there's a 50% of chance that you're going to do it wrong. And when you do it wrong, there will be a discrepancy between the oracle, the reward, the expected reward that will be achieved by the oracle policy versus the reward that you achieve with this randomized policy. Okay, and therefore the regret will occur. I mean, if you pick the right arm, the regret will be 0 at that period. But if you pick the wrong arm, there will be some regret. Always, right? So therefore, the question is, at the end of the day, is that if you want to minimize regret, it's better to do it right more than do it wrong. Okay, over time. Okay. And our goal is to learn a policy pi that, of course, this pi is past dependent. Okay, this pi can be dynamic and past dependent, depending on all the observations you have in the past. Okay, we want to learn a policy pi that, so pi is not a static policy, and you cannot do it afterwards. Afterwards, so you cannot collect the data first and then, estimate a policy pi. You have to do it, onwards when the decision-making process is going on, right? You cannot wait until the end of the experiments. Okay, right? So we want to learn a policy pi that maps VT to the decision AT to minimize this cumulative regret. So that's the sort of the mathematical formulation of this sort of dynamic, decision-making problem in general. So basically, people are always talking about minimizing regret. Okay, what's the benchmark here? So the good algorithm should have, I want to claim this, is that a good algorithm should have at most a so-called sublinear regret, which basically means that the 1 over t times the regret of t has to go to 0. What does that what does that mean? It means that think about this. If you do random decisions, so every period you have 50% of chance to make things wrong. Okay, and therefore in expectation, the cumulative regret should be a linear function of capital T, because in every period, you're likely to generate some sort of regret here, okay? So a good algorithm must be the algorithm that is doing the right decision asymptotically, okay? And therefore, when you do the right decisions more and more often, that means that you are taking the optimal actions in most of the time periods. And that's the only reason that you can have the so-called sublinear regret, okay? And how often you do the right decisions will affect the order of this, okay? And let me tell you two kinds of common policies that people has been thinking for a long time. In the literature. So let's ignore the endogeneity problem for now. So this is still the background. Okay. So assuming that there's no endogeneity problem, which means that epsilon t is independent of vt. Okay, vt is the characteristic variable. So this is a type of algorithm called greedy algorithm. So alpha hat it minus 1. So this is the parameter of reward associated with arm I at time t minus 1, estimated from the past data. Okay, so this is your estimate, and the vt is your observed characteristics right now. And based on whatever you estimate so far, of course, we know that all these estimates may not be very precise, but it doesn't matter. I just pick the best one, the best choice based on these estimated alphas. And that's my, decision at time t. So this is called greedy algorithm. Okay, I always pick the best one according to my knowledge or according to my belief right now. Okay, I mean my belief may be wrong, but I just do it. So this is called a greedy algorithm. Okay, and it can be shown that in the literature, under certain type of assumptions, it can be shown that the regret has the order of logarithm of t. So this is very small. We talk about sublinear regret here. So basically, as long as this t inverse times regret of pi t go to 0, we call it a good algorithm. But obviously, logarithm of t is much smaller than like t, right? So logarithm of t divided by t goes to infinity very fast. Sorry, goes to 0 very fast. So this is a good algorithm. Okay. Another type of algorithm that is often discussed in the literature and very popular in practice is the so-called upper confidence bound approach. Basically, you still make decisions based on your alpha hats, the mean estimate, for example, of the reward at time t minus 1. But in addition, you're going to add an estimate of the standard variable, so a standard error. So this is basically the standard error of this term, and multiply. So this is the variance. I'm sorry, this is the variance of this term, and then take the square root. So that's the standard error of this principal component, and then multiply by some sort of a theta t, which is a scalar variable. The theta t is often chosen as, for example, logarithm of the little t, something like that. And how do you think about this? So you can sort of imagine that this is the mean estimate of the reward. And this is some sort of, confidence interval length, okay? And when you add the confidence interval length to the mean reward, that's the upper confidence bound of this arm's reward. Okay, so this algorithm is telling us that be optimistic. You always pick the most optimistic one rather than, the one that has the highest mean reward, because it could be the case that some of the arms is very good, but because its confidence interval is very large, so it doesn't look like very good in its mean estimate right now, but it still have a good potentials. So you should always try the good potentials a little bit more, given some chance, right, to to the people who have to the arms that have that has potential. Okay. And you know, people show that you know, theoretically the regret will be the logarithm square of capital T, although it seems that here the regret is slightly larger than the regret you have you know, in a greedy algorithm. However, in a finite sample sense, if capital T is finite, you know, which one is bigger? You know, is you know, we don't have a very conclusive result. So it could be that in a finite sample case, the UCV algorithm can actually do better. Okay, you know, regardless of its slightly higher order in the logarithm of T. Okay. And now I want to, you know, start to talk about the endogeneity problem. And I think this is the core of this talk, okay? So I would like to have, you know, draw your attentions on this. So the standard setup of endogeneity, you know, mathematically is that, you know, the expectation of epsilon t conditional VT now is non-zero. I mean, misspecification can do this, omitted variable can do this. I mean, there are many reasons that you can have this, okay? You know, for example, you know, the omitted variable can be, you know, consumer sentiment in the, you know, like e-commerce sort of, you know, environment, right? Supposing that you are sort of selling like soccer shoes, okay? And you find out that you know, when you do advertisement in the weekend, you know, you always have a slightly, you know, better you know, sales. But that's probably because the consumer sentiment is higher in the weekend, because there are like football league matches in the weekends. You know, people watch this, you know, football you know, like England Premier, right? So you know, you watch these football games, and afterwards you feel very excited, then you just go outside and buy a pair of shoes. Okay, so that's one simple example. Ability is another one. So, you know, in labor economics, people has been talking about, you know, ability, you know, when we talk about the standard question like, you know, estimate the return to education, right? So if you ignore ability, that causes endogeneity, and typically it's gonna cause like higher estimate or lower estimate of you know, typically higher estimate of return to education. Okay, because you know, people with higher ability tends to have higher wages after graduation, and also have higher chances of getting into a college. Okay, and others. So now I'm gonna give you one simple example of what's gonna happen. When you bring these sort of endogeneity issues in a dynamic environment. Okay. Let's imagine that we have two arms, two choice. Okay. You know, you either pull arm 1 or arm B. Arm 1 is a safe arm. So whenever you pull the arm 1, you're gonna have a constant reward of little c. Okay, let's just say that. And let's just imagine that little c is known right now. Okay, right. You know, you can also do arm B. So the second arm is a risky arm. So the risky arm, let's say, is unknown, and it depends on a one-dimensional variable called little v with an unknown coefficient of alpha. Okay, you know, in the innovation literature, people has been talking about these sort of setups quite a lot. So you have a safe arm, which is the like traditional organizational structure, for example, or traditional technology, and you can choose to innovate or not. So it's like you know, whether you want to do this experiment or not, and you want to learn about you know, what you're gonna get, you know, when you switch to the other one. Okay. And you know, the reason that we're doing this example is that basically it's very simple to figure out what's the Oracle policy in this context, right? So the Oracle policy is to pull arm 2 if and only if alpha little v is greater than little c. Okay, if alpha is known, right? Of course, alpha is unknown, so we have to estimate it in practice. Okay, so here's the interesting thing. Imagine that this agent is using some kind of a greedy algorithm. I mean, just like the kind of greedy algorithm we have just described before. Okay, so you have estimate of the alpha, and you make decisions based on your best estimate of alpha so far. Okay, I mean, that's the sort of the core of all algorithmic decision making. You know, you estimate some models and you make decisions based on that. So you're gonna select arm2 if so this is a simple algorithm that suppose this agent is gonna implement. Okay, you're gonna select arm2 if alpha hat t times vt is greater than c. So this is your estimate of the alpha. This is what you observe, and this is the cutoff value. Okay, so this is a simple rule, right? And before we talk about, you know, like complex algorithms, let's imagine that this, you know, this agent is simply running like ordinary least squares, okay, which is supposed to be the most powerful tool in social science, you know, for us. But you know, so the alpha hat t plus 1. So this is so here is the updating rule that how we estimate these alphas. Okay, so alpha hat t plus 1 will be the outcome of an OS regression by adding this additional observation of data to the pool. So basically, you know, you only have one more data when you pull the arm2. If you pull arm1, you have no new observation, and therefore you have no new information, right? So if you if alpha hat t vt is greater than little c, if this criteria happen to hit, then you're going to update your estimate using this new data point, okay? And presumably you're going to have a better estimate. Otherwise, you're going to stay the same because you have no info, you know, you have no new information of the alpha, right? Of the parameter alpha. So that's a simple rule, updating rule. So, you know, you can see this is the dynamic decision rule here, and this is dynamic learning rule. Okay, so two rules, okay? So, you know, again, I want to emphasize that the data used for estimating alpha is only available when you pull the arm2, okay, in this case. And therefore, suppose the alpha hat t will converge to some parameter alpha hat in the long run. Let's just say that. I mean, there's a chance that the alpha t doesn't converge at all. Or it can be like cyclical, you know, jumping around. It could be possible, but now we're only studying the path that you know, the alpha converges. Okay, if it truly converges to a stable point, then, you know, according to the simple formula of linear regressions, we should have this, right? So the alpha hat should be equal to alpha plus the covariance of vt epsilon t divided by the variance of vt. So that's the, you know, that's the like, you know, econometrics 101. When you have like one single variable, but here we need to conditional on this event, because only when this event happens asymptotically, right? Because alpha t will converge to alpha hat. So only when this event happens, we have some of, you know, observations in the arm2. So therefore, this is a formula that you know, this is simple linear regression formula that's conditional on the, you know, on the events that you actually pull arm2. Okay, so that's the main difference compared to, you know, standard. So if you randomize your decisions, then the standard OS should give you this. So the OS bias will be the covariance of VT epsilon t divided by the variance of VT. And in the context of dynamic learning, you know, you are still computing the covariance of VT epsilon t divided by the variance of VT, but conditional on the event that VT is larger than C divided by alpha hat. So that's the main difference of the two. Okay. And you can see that in the dynamic environment, because of your dynamic selection rule, the data point you observe is only a subset of all the data that you generate. And this subset, of course, itself is dependent on the parameter that you estimate. Okay, and that's how, you know, we call the self-fulfilling bias, because your policy affects your data collection process, and your data collection process affects your estimate of the parameters, and in the end affect your policy. Okay, so that's the key point. And one of the way to interpret the, you know, the limit alpha hat is to interpret it as a fixed point. Okay, so on the one hand, the agent is learning from the past, and therefore the agent has a belief of the reality. On the other hand, the agent makes decisions. And at the end of the day, the decision must be compatible with the belief. And that's a fixed point. Okay. So unlike the traditional sense is that, we just sit there, collect data, observe. So we're not decision makers. So we simply evaluate what happens in the data generating process. But now when you are actually a part of the DGP, right? So, your decision and your belief, now has to converge. Okay. Right. And here, one simple phenomenon, one phenomenon we find out for today. One phenomenon we find out in our research is that this alpha hat as a fixed point of this equation can actually have multiple values. That means that you can have multiple fixed points. Okay, so for example, this is what we call it as PPD among SSE in organizational economics. Okay, so it's called positional performance differences among similar enterprises. Okay, so one question that has been puzzling for scholars who study organizations, for example, firms or universities, is that these firms, they started to be very, very similar to each other. These universities, they started to be very, very similar to each other. But how could it be that, gradually when time evolves, their organizational structures are so different, their policies are so different, and why is that? So this is one of the key questions in organizational economics. Okay, and here we want to link the phenomenon of basically this sort of self-fulfilling bias to this PPD among SSE, okay, phenomenon. Okay. So actually there's one question from Sunya Deep. Let me ask the question first, and I will continue. Okay. Is the self-fulfilling bias formula an alteration of how we interpret omitted variable bias in the econometrics? No, I think it's not completely the same, because whenever you have omitted variable bias or any other kind of endogeneity, it's more like the OOS bias here, on the right hand side. So this is the traditional bias you're gonna get. I'm talking about a bias that is, of course, partially because of endogeneity, but more importantly, it's actually caused by this sort of dynamic policy, or actually it's gonna be generated from your policy at the end of the day. So your policy is part of the game. Okay, so that's my emphasis here. So that's different from the traditional way of thinking about for example, omitted variable bias. Okay, but it has it's related, but it's different.
Can I just ask a clarifying question?
Sure.
Yeah, so in the previous slide,
yeah,
so here alpha, actually the alpha is gonna be the asymptotic limit of alpha hat, right? And
yeah,
alpha is alpha the true coefficient you are?
Yeah, the little alpha here is the true parameter.
So
and
when you use okay, go ahead.
Yeah. And you can see that if you eliminate this conditional symbol, you get a standard bias formula, right? So what's difference here is that you have this additional selection criterion.
Yeah. So you're saying that when we use the OLS, the traditional OLS estimate to do it, we are actually getting a biased estimate, right?
Yeah, and this bias is different from the traditional OLS bias.
Yeah. All right.
That's what I mean. Yeah. Okay. Thank you, Tom. Yeah. So let me give you one example. So here is a here's a graph of the very traditional return to schooling sort of story. Okay, assuming that on the y-axis that's the return of education, And on the x-axis is the, let's say, SAT score, okay, of test or whatever the, test scores, of college entrance exam, examination scores. Okay, assuming that there's this sort of, a slightly complex nonlinear pattern between the two. Okay, so what's going to happen? So this little c here is the benchmark policy. I mean, for example, you just randomly admit, okay, whatever. So, or maybe you just, you can admit everybody when the score is higher than S little star, okay. But think about what's going to happen. So when you admit these students, and then, these are going to be the students that you observe, okay. Then you run a linear regression to estimate the return to schooling when you admit these students with high score, but you figure out that here if you take this part of students and you run regression, the slope coefficient is here. So this blue line. So you figure out that the slope is very low, and therefore it will solidify your belief that admitting high score student is the right thing to do, because only by doing that you can guarantee that these students will have a very high return after education. Okay, right? So on the other hand, suppose there's another university that has this like a very low bar of test scores. Okay, and then they're going to observe all the students above this above this bar called S capital L, and then again the people here also run a regression, and then they figure out that now this orange curve will be the slope when you run regression using all the data points that's that has a score above SL. Okay. And because your estimated slope is higher, then you believe that actually getting this low score student doesn't matter, right? As long so this will also justify the policy to use low score to serve as the cutoff value as well. Okay, and therefore this is sort of the self-fulfilling story we want to tell in economics. Basically, if organizations, they make decisions based on what they observe, they learn from what they observe, and in this case, it's a simple model misspecification, problem that you are modeling the return to schooling as a linear function, but actually it's nonlinear, right? So this is one kind of endogeneity. If you do that, this story can be, self-justifying. MIT has very high, standard of SAT admitting scores, and they always, recruit these like high score students. And maybe some other university has a very low bar, but they can all justify themselves. And therefore, this is one, one potential reason that why, different organizations in the end, end up with a completely different, like policies, for example, just because these are all these are all fulfilling, right? So you observe this data, you estimate, and you find that your policy is right. Okay. In terms of the numerical illustration, we have this joint distribution we call the glowing worm between the residual epsilon t and VT. So suppose that's the case. Okay, so you have some kind of, so on the right hand side, this is a density. So you see that, it has two modes, right? And the VT is uniformly generated. And given that, joint distribution, actually we can create like 3 fixed points. Okay, so the truth of alpha in our numerical experiment is 15. If you run OS, you get 17. So you should have a like upward bias when you run OS in this case. Okay, and we track all the alpha t path over 10,000 periods. So if you just do this sort of greedy algorithm and make decisions according to, so if you make decisions according to this greedy algorithm and you use OS to learn, so you're going to end up with, these kind of path of alpha t's, okay? And you can observe that a very big mass of the alpha t paths end up with a point around 10. So that's the fixed point number 3, okay? So this is one fixed point, okay? Where the beliefs and the decisions are compatible with each other. Another fixed point is 5, but this is actually an unstable fixed point, and the algorithm will gradually deviate from 5 and converge to either 10 or the other fixed point 2, when this initial estimate is at 5. Okay, so we have got 2 fixed points here. One is 10, the other is 2, and both of these fixed points are self-fulfilling. They are self-justifying. Okay, so that's what we found. In fact, you can have multiple equilibriums in this case. Okay, and of course, these so this kind of multiple equilibrium can also appear when other kind of machine learning algorithms like upper confidence bound or whatever are used. So if you don't address the endogeneity problem, you're going to end up with these sort of issues. Okay. And the implication of self-fulfilling bias is the following. First of all, the frequency of a wrong action being taken is proportional to capital T, which means that you're going to have linear regret because your limit estimate of alpha is biased. So it's very likely that you're going to make wrong actions pretty often, right? The second one is the multiplicity. The agents may adopt different policies even if the underlying production environment is the same to start with. So the perturbations of the, so different jaws of the epsilons and v's in the beginning can actually lead the entire path to completely different fixed points. Okay. And actually, we have anything goes theorem. We prove that you can have arbitrarily many number of fixed points and arbitrarily, distributed alphas, arbitrarily distributed, distributed fixed points as you wish. If the, copular, of the distribution of like epsilon t and vt are complex enough, you can have arbitrarily complex kind of, distribution of these fixed points. Okay. And now I would talk about the instrument variable approach. So when the VTs are exogenous, then we're gonna have reward RT, which equals to little c times indicator of AT equals to 1 plus alpha times VT times indicator of IT equals to 2 plus the epsilon t. Okay. So of course when VT is endogenous, then you still have this, but I want to say that so if VT is endogenous, because ultimately the alpha t will be a function that depends on VT, so the AT will also be endogenous at the end of the day. So we call this sort of phenomenon as so-called endogeneity spillover. Okay, so in this slide I use this like little green, so this green color to represent the exogenous variables and use the pink color to represent endogenous variables. Okay, however, if VT is endogenous and you randomize your decisions, so if the alpha t's are if the ATs are fully randomized, then these indicators functions will will go back to exogenous variables. Okay, so in the long run, because you don't want to have linear regret, so the AT in the long run will have to be a dependent function of VT and therefore become endogenous as well. So the endogeneity in this problem will spill over from the variables, the contextual variables, to the decisions. So not only your variables are endogenous, but also your decisions will be endogenous in the long run. Okay, and therefore our main point here is that if you want to apply IV, instrument variables, to estimate these sort of equations, not only you want to instrument for VT, but also you want to instrument for AT as well. So you need double instrument here to cure the problem. If you go with the instrumental variable approach, of course, you can go other approach like control function approach. You can go with, if you assume some kind of normality and you model as dynamic slashing, you can go with the Heckman device approach, whatever. But in general, if you want to apply IV, right? So imagine that you have an IV for VT. You want to have a double IV because you also need to IV for these indicator functions as well in the long run. Okay. In the short run, if you randomize, you don't need. But in the long run, if you want to keep the regret low, you need more instruments. Okay. So that's the key message in terms of its techniques. And therefore, so I wanted to start to discuss, our way to solve this problem. Okay, so imagine that you do randomization first. Okay, when you do randomization, you can, make these indicator functions to be, exogenous, right? So, assuming that the IV of ZT is available, then you can do two steady squares to have a consistent estimate of alpha in this equation. So that's no problem, okay? That's the good thing. You can estimate alpha very well if you just keep on doing randomization and with instrument variable by 2 SOS. But the problem is there's economic cost here. The regret is very high because if you randomly choose arms, then, you pay a lot of the cost. So you want to do the right decisions over time. And at the same time, you want to learn the right thing. Okay, so that's the goal. And therefore, we propose our, so-called Ivy-Grady algorithm here. So the Ivy-Grady algorithm will have 3 phases. Okay, and I use like capital T1, capital T2 to sort of demonstrate the length of these phases. Okay, so the first phase will have a length of capital T1. Basically, in the first phase, we just do randomization. And then we run 2 steady squares to estimate a preliminary estimate of alpha. Okay, so that's what we do in the first phase. We call it like random exploration. Okay, so you want to start with a good initial estimate first. Okay, and then in the phase 2, again, so the phase 2, the length is T2 minus T1. Okay, and then we just take greedy actions based on our estimate of alpha hat of T1. So this estimate is the terminal estimate of phase 1. You run 2 SOS, you estimate this alpha hat T1, and you just fix your estimate for a while without updating it. Just fix for a while. The reason to do this, we call it covariance stabilization, because you want to generate enough number of data points that contains information of the endogeneity of the indicator variables. Because remember, in the first phase, all the actions are randomizedly chosen. So therefore, so these indicators will be completely random. But in the second phase, your ATs will be generated from a policy that dependent on VT. And therefore, we want to draw a number of data points that has this sort of pattern. Because the AT here, the key is that in the second phase, the data generating process of AT is different from the first phase. The first phase is randomized, okay? And then, after you have enough number of data points, in phase 3, we start to learning and making decisions continuously, okay? We take a greedy action with parameter updates. So AT will be chosen as the maximizer of the, of the best estimate you have, at time t, right? So this is the estimate of alpha hat I at time t minus 1, okay? And then after you do this, you collect the data and run the 2 steady squares from T1. So basically, you're going to include all the data you get in phase 2 together with the new data you get in phase 3, all the new data you get in phase 2 at any time little t. And then you do a 2 steady squares. So this is a 3-phase algorithm. Okay, this is three-phase algorithm. And we claim that this three-phase algorithm can address the problem. I mean, this is a formal sort of, view of the algorithm and how it works. In the beginning, we have a so-called coefficient stabilization. So you randomize and you have a pre-estimated alpha. And then the second phase is covariance stabilization. You draw the alpha, you draw the ATs due to the greedy algorithm, but based on the estimate you have before. So this is your estimate at terminal phase 1. So that's what you get. And then third, we do the policy improvement. Okay, so we just keep on doing this. And potentially this can be a UCB algorithm or greedy. So if you set the sigma parameter to 0, that's going to be, if you set this little theta to 0, that's going to be the greedy algorithm. Right? If you set little theta to 1, that's going to be the UCB algorithm. Okay. And I want to briefly introduce the theory. Then I will jump to I don't have time to discuss all the technical details, but I will then jump to simulation results, and I will leave some time for questions. Okay, we can prove that if you do the three-phase algorithm, okay, and you pick this capital T1 to have some sort of order of logarithm of t, and the capital T2 also have a logarithm of t order. Why is that? Remember, in phase 1, you randomly pick the decisions, and therefore it's very costly. Okay, so if you want to have a very low regret, the phase 1 cannot be very, very long. Okay, and similarly, the phase 2 cannot be very long because the phase 2 employs a greedy algorithm that's based on the estimate from phase 1, but since the phase 1 does not have too many data points, so the initial estimate of the phase 2 will not be very precise as well, and therefore you don't want to have very long phase 2 as well. Okay, so here we will limit the length of phase 1 and phase 2 both as logarithm of capital T. Okay, for some sufficient large constant C1 and C2. Okay, and then every greedy algorithm will satisfy the following. So first of all, we have a central limit theorem. We can show that the terminal value alpha capital T minus the true parameter alpha will converge to some normal random variable, blow up by the square root of t minus t capital T1. But remember, capital T1 is very small compared to capital T. Okay, so this is essentially root t asymptotics that you can show. So on the one hand, this algorithm will guarantee that you're going to have root t convergence of the estimates. But on the other hand, we can show that the regret will be the order of logarithm of capital T. So this is good in the sense that basically you have the minimax rate of regret, because one can show that in general the regret cannot be smaller than the order of logarithm of t. Of capital T. Okay, so this three-phase algorithm will attain the lowest regret in its order, and also you can learn it asymptotically correct and with the central limit theorem here. Okay, as I said, the most difficult thing here is that basically I just want to spend 1 minute on this slide. Okay, so this is the standard formula for two stages these squares, right? So the key difficulty here is to analyze the behavior of phase 3. So basically, this is the 2SOS formula. If you are not familiar with, don't worry. Here are the decompositions of these things. Okay, the first thing is where ZT is the instruments, right? So this matrix is basically the ZT transpose. This is the empirical covariance matrix of ZT, and we want this matrix to be well behaved, which is easy technically. And this G hat, which is basically the sample average from little t1 to little t2 of ZS times epsilon S. Remember, Z is the instrument variable and the epsilon is the residual. So this should have a central limit theorem, and that should also be easy. The difficulty part is this. So, this sigma VZ, the covariance matrix of V and Z is the following. So you have this V tilde and the ZS, where V tilde is this, right? So so basically these ATs are the difficulty things to analyze because ATs are generated by dynamic decisions. So the AT is not generated from you know, quote unquote like IID fixed DGP, but rather is data all these actions are, you know, past dependent. It depends on the entire history of the past. Okay, and therefore, you know, the analysis of these matrices are somewhat challenging, in this problem. Okay. Okay. I see several questions, but I will answer these questions afterwards. Yeah, thanks. So I jumped all these technical parts and you know, I just want to make a few conclusions on, you know, on what happens. You know, we want to link proof a little bit with the algorithms. Okay, so first of all, the first thing we want to claim that you know, the two-stage least squares, that the naive two-stage square does not work, because the naive two-stage square does not take care of this, you know, endogeneity spillover problem, because here all the actions are endogenous. So you want to instrument for the actions as well, not just the V's. If you use ARM specific data and then run two-stage squares there, it's going to give you very biased results. Okay, and the second, you know, in phase 2, we want to do this you know, very specific phase 2 in the algorithm, is because we want to ensure that you know, we can stabilize the link, you know, the covariance between the indicator functions, you know, those actions with the instruments. Okay, we want to ensure these two are stabilized, because the actions are somewhat past dependent. Okay, so we want to have a mechanism that ensures that these two will collide into each other in the long run. Okay, and in the end, I'm going to show you some simulation results. I will end our, you know, my share for, you know, for a minute, and you know, because I want to switch to another source. The PDF will be broken when I make you to the pictures. Okay, just 1 minute. Okay, so this is you know, a document on the website which does not have the, you know, PDF problem. You know, so the simulation setup is the following. So you know, we have a VT that's like 3-dimensional, a constant, an exogenous variable xt, and a endogenous variable called dt. Okay, and the dt is the following. So dt will be correlated with the epsilon t through this eta t channel, right? This eta t will be the correlation channel, but also this dt is somehow correlated with xt as well. So it's not completely independent of xt, remember? So this makes things a little bit, you know, slightly more complex. And the reward function here, we will estimate as a linear function of a constant xt and dt in general. So this is a mean reward function. Okay. And as I said, you know, here, suppose we have a ZT VEC to serve as an instrument for DT. But because of the endogeneity spillover problem, so we want to create a bit more number of, you know, ZTs, right? So, you know, instruments. Here, we're going to use some like nonlinear transforms of the exogenous variable xt's and zt's. So basically, the assumption is like a conditional, you know, it's like a conditional moment condition, right? So, you know, these instruments, you can do some kind of a nonlinear transforms, and you can form new instruments from there. Okay, and here, and in the end, we have 9 instruments in our experiment. And this picture will show you what's going to happen if you do different kind of algorithms. Okay, so you know, the blue one here is the Ivy Grady, which is the like the most ideal algorithm that we want to show you. So this Ivy Grady algorithm, as we as we demonstrated in the previous slides, has a logarithm of t regret. Okay, and also this orange line is the IVUCB algorithm, which is also pretty good in terms. I mean, you can see that although in the beginning it's pretty high, but over time it has a logarithm square of capital T regret. And if you look at others, right? So this red line is so in the beginning, this is the randomization phase, and then everybody starts to evolve according to his own logic algorithmically. This OS algorithm is gonna have this it's gonna have this red line, which is gonna be linear regret at the end of the day. And this green line is naive IVUCB. This is the case where you run two series squares in the arm specific fashion, which will lead to completely wrong estimate actually, because you need to control for the endogeneity of the actions as well. Okay, that's why we call dynamic selection, because here the action is selection. Okay, this purple line is called RTC. We call it randomize then commit. You can always randomize for a while, and then you run to SLS. You have a more or less consistent estimate. But as we said, you cannot randomize for for a very long time, because otherwise your regret will explode. And therefore, you randomize for a while. For example, you randomize for for the order of capital T to the 1/2 time, okay, T to the 0.5 order. And then you just keep on doing this, using this estimator for the rest of the entire period, experiments, and you're gonna have this purple curve here. Okay, it's better than the naive IVUCB, but it's still we can show that it's sublinear regret, but it's not very it's still a fractional polynomial rather than logarithm of t. Okay, and on the right hand side, you can show that we run a regression of regret on the logarithm of little t, regret of little t on logarithm of little t, and we find out that in the long run, so these are the observations. In the long run, we have an R square equal to 0.99, so which means that we have basically a regret of order of logarithm of t. Okay, in the linear sense. And when we run, the IVUCB regret on logarithm square of little t, we have an R square of 0.88, which also sort of verifies our theoretical proof. So in the long run, you're going to have logarithm of regrets, okay, for both experiments, okay. And this picture will show you the estimates, as you can see here. It's probably a little bit big. The Ivy-Grady algorithm is the blue one. You can show that gradually it's going to converge the true parameter in so we have 6 dimensions, gamma 1, gamma 2, the 2 betas. So these are constant estimates, the parameters, and these are the exogenous variables, and these 2 gammas are for the endogenous variables. Okay, so the Ivy-Grady and Ivy-UCB will produce consistent estimate in the long run. But all of the other algorithms, they will produce more or less biased estimate. This naive IVUCB is actually, extremely biased. Okay. And in the end, let me conclude. Then I will leave a little bit time for questions. Okay. So in online learning algorithms, the endogeneity in data will spill over to actions and resulting in the full self-fulfilling bias. So, we talk about self-fulfilling bias, and here, the mechanism that we believe that generates this is because of the interaction between decisions and the learning process. Okay, and you can imagine that this is everywhere now in our, among us, right? Among us. So, recommendation systems, job hiring, and so on and so forth. Okay, and we propose a set of Ivy-based algorithms to resolve this issue. But these Ivy-based algorithms are not vanilla, arm-specific two-stage squares, but rather it's we need to control for instruments. We need to instrument for the actions as well. So because of the endogeneity spillover effect. Okay. And third, we provide a set of general techniques that untangles the interdependence between data and action. I didn't talk too much about this. This is more technical. And lastly, the most important message here we want to deliver today is that, most often when you talk about the company policies, like when they do A/B test, like what Qin Liang asked before, right? A/B test. A/B test is like the randomization within the system, which we call the ex post randomization. Okay, so in a system you can choose arm 1, arm 2. That's okay. So you can randomize, you can learn. That's okay. But no matter how much you randomize, you do not resolve the endogeneity issue. Okay. You can learn, but you may have like very biased learning. So that's called ex post randomization. And in terms of understanding the causal effect of decisions, here we will advocate companies or firms to use more of the so-called ex-ante randomization. And in this case, ex-ante randomization will be the instruments. For example, the firms can shock, on a higher level of firm structure to understand what's going on in the lower level. Just like the advertisement campaign story I've talked about. You can launch an advertising campaign on your own website, but you need to control for consumer sentiment. And how do you control for that? For example, you can randomize the money that you pay to Google search engine, right? When you randomize the money you pay to Google search engine, your rank may be different. And that creates an ex-ante randomization, which shocks the entire system. And that will be the instrument variables that we are seeking for here, okay? And it's very different from, in terms of the aspect of, a social scientist versus, a business owner, is that usually social scientist has a very painful, experience of looking for instrument variables, because we don't have the control on the DGP process. We just collect data and we try to find some smart IVs, okay? However, when you are a firm owner, when you run a business, you can always randomly shock some part of the firms. I mean, some of the variables are going to be very expensive to shock, like the prices are usually very, very, highly costly to shock. Okay, not only because it's going to create suboptimal pricing, but also it may hurt your reputation as well. But you can shock on other things, right? For example, rebate or any kind of promotion plans is a kind of shock that you can give. Okay, that's called ex-ante randomization. Okay, so that's what I want to deliver here. And now I'm happy to answer the questions. Yeah.
Thanks, for all this very insightful. We can discuss more afterwards. Now it's the Q&A session. So according to the queue, welcome Professor Tony Tam from Sociology. Please, Tony.
Hello, Kurt.
Hello, Tony. Nice to see you.
Thank you so much for your talk. It's fascinating, even though almost nothing in your title seems to attract sociologists' attention, except the first adjective, self-fulfilling, is one of the most famous classical contemporary theories in sociology. But nonetheless, I have a simple question.
Of course, yeah.
And if the answer is yes, I have two follow-up questions. My simple question is, what if Darren H. McGrew is writing your paper, the technical part? Could he have write a paper on state policy, comparative government behavior, using your self-fulfilling bias as the anchoring point? If the answer is kind of yes, then I have two follow-up questions.
Okay.
Among the so-called implications you derive from your model, there's only 2 points on one of your slides, drawing 2 implications, none of which seems to be particularly concrete and down to earth, with implications for how to detect the presence of self-fulfilling bias in a certain policy regime.
Yeah.
The second question is, of the so-called remedies you recommend to machine learning situations, you have a solution, so-called algorithmic solution. What if it's in the context of state policy regime? After detecting that, like Hong Kong government in response to the COVID-19 pandemic, or the Chinese government in learning to how to reform its science policy, it's detected that there's confirmation bias. Can your algorithm be translated into so-called concrete, meaningful policy recommendations for them how to learn better, do better? So those are the two follow-up questions. If the answer to the first one is yes. Thank you.
Okay, I mean, thank you very much, Tony. I think the answer is definitely yes for your first question.
Okay.
Confirmation bias is definitely related, but we're talking about a bit more than confirmation bias, because we're talking about further interaction arises from confirmation bias. Because you confirm, you make more decisions, and then you confirm again. So that's kind of additions to a bit more than just confirmation bias. Yeah, but then the two follow-up questions are very good. In terms of, I understand that the sort of the focus is a bit different, because I mean a lot of sociologists, like you said, maybe focus on like governance. In this paper we talk a bit more about our examples are all maybe more in a business environment, especially in a digital economy. But I would totally agree with you that there's a possibility for the government to do something like this. First of all, we need to detect whether there is this kind of a self-fulfilling bias. My personal thinking is that this is probably everywhere. According to my understanding of organizational economics, I mean, because government is also a kind of organizations, okay? And how do you detect or statistically test it? I think that's a good question. I mean, my answer would be shocks. You do shocks, some kind of shocks, like the IVs here. And then you can compare your estimate with and without shocks. And if you have enough data over that, you can always do some kind of statistical test to show whether there is this kind of confirmation bias or self-fulfilling bias in the government. The question is, how costly would that be? I mean, when we talk about economics, it's always about learning and cost. If it's too costly, then maybe we will just stay with the biased policy anyway, right? They can be economic costs, they can be political costs. Okay, and secondly, how do these organizations, how can they do to correct for it? The kind of organization that I'm familiar with, which is most similar to the government, is, for example, the central banks, Federal Reserve, let's just say. In fact, I think I have talked to a lot of macroeconomists, and we believe that it's possible to incorporate some kind of mechanisms like this into their learning process, because if the macroeconomists will basically make decisions based on some kind of structural models with their own domain knowledge, and they have estimates of what's going to happen. But of course, you have still have this sort of problem if you, for example, if you misspecify the models, right? So there still can be this kind of risk, and therefore the answer is that you may want to randomize a little bit of your policy. I mean, not all. I mean, maybe you don't want to randomize your monetary policy because it's too important, too costly. But in terms of some of the fiscal policy, for example, let's say that Hong Kong government give like 5,000 HKD to all the residents, in the past couple of months. Of course, that's very good, right? So if you can randomize the time, or if you can randomize, a bit on the amount, you don't have to pre-claim that it's 5,000, because it's going to form some kind of expectations, right? So if you can do some shocks, it doesn't have to be the shock that is directly related to the variable that you care about, but it can be other shocks as long as it's correlated through some mechanisms and it's tricky enough. You can still do that. And here will be the IVs, that you need, and you can still somehow more or less estimate. Of course, how to build a model will depend on your domain knowledge. That's my answer to it. Yeah. Okay, thank you very much.
Yeah, thanks. The second question comes from Rixuan Liu, Professor Liu, who is from the CHKB school. Rixuan, please.
Okay.
Hi,
nice.
Nice to meet you. Sorry, I missed the introduction part. So I'm just wondering, so what happens if you have multiple arms, more than two? So is that mainly a notation-wise complication? Because I think the decision rules are a little bit trickier. Or how does that? How would you extend your algorithm to?
Yeah. So we in a formal paper we do have a multi-arm, general multi-arm version, for the general audience. But in today's talk, I try to make the intuitions clear. So I sort of stay with 2 arms. But you're right. So in a multi-arm case, typically the regret will be increasing along with the number of arms, and the learning will be slightly more complicated as well, because because we need IVs here. And as I said, I think the biggest complication is the following. So basically, the key point, one of the key points I have made in the talk is that the endogeneity spillover. So basically, the endogeneity of the state variables will spill over to the actions. But assuming that you have more arms, that means that you have more endogenous actions along the way. And as a result, you need more IVs. And sometimes it can also cause some of the IVs to be very weak as well. So you may also have weak IV problems as well. So that causes additional estimating problems. Yeah, but we have but in the paper we do have a more general setup and along with the slightly stronger assumptions. Yeah. Thank you.
Thank you.
We have one more question from Professor Thomas. Jacob, please.
Hi, thank you for your presentation. I'm wondering if you can take into account because I think people in different substantial fields would use this sort of framework very differently. And if you can help give us some kind of contextual parameters, and one very important relevant one I can think of relevant to some of the cases you've been mentioning is kind of reminiscent of and Talk of Love. Anne Swidler writes about how she talked about ideologies, not sort of learning things that you're talking about, but I think it's relevant where like in unsettled times, ideologies are more coherent, whereas in unsettled times, they're more in flux. And so there's more fluidity in terms of the cultural repertoires people use. It's a cultural sociology parameter. So I'm wondering how you would operationalize that in this framework, because in settled times, there's a certain periodicity or stationarity to a lot of patterns you're observing. And so it's quite easier to just parameterize it with some known parameters. But in unsettled times, there's known unknowns, there's unknown unknowns, and this really complicates things. And you bring up COVID-19. To be sympathetic, I don't know if the CCP or the doctors who tried to warn about COVID, or people in the CDC, much less politicians or media pundits, knew much of anything they were talking about with COVID-19, because it was a new thing. And guess wrong or right. And so I think it'd be helpful for you to think, and with relation to inflation, like the big question now is like, how high do we need to raise the interest rates to break the back of the self-fulfilling expectations that can lead to wage and price spiraling out of control? And that's like, we could look back to 1970s, but we don't live in the world in 1970s anymore. We live very different world.
Yeah.
So, does Powell have to go full Vogler? Well, we don't know how far they have to go, and that's a big debate. But I'm just saying that figuring out a way you can parameterize kind of settled versus unsettled times, just to take one metaphor, you can describe it differently, would be a very interesting way to add another layer and help people apply this to their specific substantive field, which may vary along that parameter.
I mean, yeah, I mean, Jacob, thank you for your question. You know, I think you make a very interesting point. You know, we have been thinking about this for a long time, actually. So, you know, somewhat linked to what you said, right? There are uncertainties, and that's why we want to do learning. Okay, of course, you know, you know, today I'm talking about a bit more on machine learning, but not very complicated machine learning. But anyway, so where, you know, a lot of algorithms are learning from the environments. But there are things that cannot be simply modeled, or maybe they're just things that are mismodeled. I mean, it can be could be either way, right? So that's a source of endogeneity that we always talk about in economics. Maybe, you know, sociologists have different words for that, but you know, economists will call it endogenous. You know, the endogeneity issue. So you know, models are not perfect, of course. You know, in the worst case, you have unknown unknowns. And therefore, you know, I mean, by definition, unknown unknowns are the things that cannot be modeled. You know, ambiguity. Okay, you know, unfortunately, you know, the machine learning does not really have power to deal with unknown unknowns so far. So everything has to be modeled in a probabilistic model in some way. I mean, it could be mismodeled, but it has to be modeled in certain ways, because at the end of the day, its decisions cannot be ambiguous. Like, you know, our decision actions here, AT here, has to be something that has to be determined and be made at every time, right? So yeah, like just said, I mean, evaluating like you know, for example, you know, inflation impact, you know, it could involve some sort of learning process, and you know, if the learning process really approximated, but you know, it can also be the case that the learning process does not really approximate well, or it can be completely wrong. Yeah, these are all possible possibilities. Yeah, but to my knowledge, you know, you know, so far the best thing you can do, you know, I mean, it's a problem of methodology, and especially in social science and economics, you know, counterfactual is the best thing we can do, right? You know, even if we do it not in a very precise way, but you know, being able to do it, it's always better than not being able to do it. Anyway, yeah, yeah.
All right, so thanks. I
Yeah.
have actually one question.
Sure, yeah.
Host the sync, and now I can use my privilege. So my question relates to the fixed points. I kind of interesting to observe that you might have different fixed points toward the end for the alpha for the policy. I mean, as econometrician, the first thing we consider is probably the identification. I couldn't help but relates this to the identification of the model that's supposed to have different kind of those fixed points toward the convergence. I mean, wouldn't that affect kind of the problem you study in terms of the optimal policy, or in terms of the algorithm? If I use, let's say, different initial value or different length of T1, right, to do my randomization, different type of greedy algorithm, if I end up with different kind of convergence points, and so that's my question. Thank you.
Okay, thank you, Qinliang. So I think this is very critical, and I didn't really have a lot of time to explain the mechanisms of the algorithms in detail, but like I said, like it's a three-phase algorithm, and why we want to have this complicated design rather than just going forward directly is because of what you said. Initial values matter. And we have run a lot of experiments, and if you start with random initial values, the algorithm can just fly out and get to nowhere. So that's very common, right? So this is also a issue of algorithmic robustness, where people does not pay too much attention to it so far, is that a lot of algorithms are very, it looks like very nice, but whenever you bring it to this kind of dynamic scenario, there's a chance for it to not to converge. Yeah, due to all kinds of reasons. In terms of algorithmic design, we want to make it more robust, and that's why we designed the first phase and second phase, because the reason to add second phase is also similar, because in the first beginning we don't have that phase, and then sometimes you get lucky, you have convergence and you have consistent estimate. Sometimes if you're unlucky, you get a path that goes to infinity. Okay, that's possible. Or go to some some kind of weird spot. Okay, so therefore these are critical parts of algorithms that we need to care about. I mean, it's not really completely vanilla 2 squares anyway. Yeah, yeah, I mean, actually understanding the dynamics of this sort of process, I think, is the key for the analysis of dynamic algorithms, because unlike the traditional statistical or econometrics, whatever the analysis you want to do, you collect data first and you estimate in the end. So more or less is static, and people don't care about the process. We only care about the terminal value. But when we think about the dynamic environment, the entire process matters. That's why it's called machine learning. Learning ends up with an ing word, so it's something in action rather than estimation is something that only has a result or consequence. Okay, so yeah, that's so your question is very important. So yeah, we do suffer from this, and that's why we have this specific design. Yeah.
All right, thank you very much. Now, thanks everyone for attending our CSSL webinar today. Let's give a round of applause to our speaker, Professor Luo Ye. Yeah, thank you very much. Look forward to see you in person in the near future.
Okay, yeah, of course. Thank you very much. Look forward to seeing you.
Thank you. Thank you, everyone.
Bye.
Bye.